Greetings, chemists. This will be the last lecture in the series on solutions, until I think of some more lectures, I suppose. But we'll be talking about how dissolved particles affect the solution itself. And so we'll be looking at various different kinds of ions. Most of the solutions that we will make and use in our chemistry class will be aqueous solutions, and so most of the things we will be dissolving in them will be ionic, because ions and water get along really well. We'll talk about what makes a strong and weak electrolyte and how that affects the boiling point of the water and how it affects the freezing point of the water. So to start with, let's take a simple thing like sodium chloride, that when you dump it into solution, it dissolves. We can actually write an equation for sodium chloride dissolving. So let's take this. Let's draw it first. Let's take a solution of sodium chloride, a beaker of water and a bunch of salt particles that I'm going to dump into that water. So up here, it's NaCl, and it's solid. It's a crystal. And it's going to go into the water. The water is just pure H2O. And we'll mix it around. And when it's done, we will have a bunch of now, I could draw them. There's going to be some sodiums. There's going to be some chlorides. They're all going to be jumbled. They're not going to be connected to each other anymore. They will have dissolved. They will have mixed in with the water. We know how that works from the polarity video. And this will be the solution. Now, this is not technically a chemical reaction. The reason I say that is the sodium before was Na+. When it gets into the water, it's still Na+. It's just mixed around. This is a physical process. Dissolving doesn't actually change any chemical bonds. It just sort of allows the mixing of the atoms, right? But the atoms themselves are all still the same as they were before, right? So here's how I would write this. I would say NaCl, that's one of my quote-unquote reactants. It's one of the participants, and it's a solid. I'll put a little S there, right? And then it's turning into, we're adding it to water, and it turns into Na plus aqueous, because now it's no longer solid, plus Cl minus aqueous. Also, there's still a bunch of water molecules. Now, water appears on both sides of the equation. It's a liquid. I should put L for liquid if I'm really being correct. And because it appears on both sides, we usually ignore it. So we would call this is what's referred to as a net ionic equation. We would have a sodium chloride solid, and it dissolves, and it turns into sodium plus ions, and it turns into chloride minus ions. Now, just like any other equation, we would have to balance this. Although notice there's one sodium here, one chloride here, one chloride here. So it actually is balanced, okay? Just because these are 1-to-1. So not a big deal. And you can use it like any other chemical equation. You could say that for every 1 mole of sodium chloride that dissolves, you would get 1 mole of sodium ions, and you would get 1 mole of chloride ions. And that shouldn't be too surprising. Now, this changes. Let's do something like a calcium chloride. If I did the same process, but the salt that I'm dissolving is CaCl2, that's calcium chloride, and I get all the particles in here, I could write an equation for this guy dissolving as well. Well, it would be calcium chloride as the solid, and it would start off as a solid, and it would turn into, I would get calcium ions, which are +2 ions, and they would be dissolved in water, so they would be aqueous. And I would get chloride ions, and chloride ions are -1 ions, and they would also be dissolved in water, so they would be aqueous. The difference is that when I go to balance this, it's no longer balanced. It does have 1 calcium and 1 calcium, but it has 2 chlorides here and only 1 here. So I would actually have to put a 2 out front to balance this reaction. I say reaction, this equation, this net ionic equation. So what does this tell me? If I were to dump 1 mole of calcium chloride into my water, I would get 1 mole of calcium ions, but I would get 2 moles of chloride ions because there's twice as much chlorine as there is calcium.
Dalton Slavin, please report to student services. Dalton Slavin, please report to student services.
Sorry for that interruption. So, all right, let's see how that works then. if I were to take exactly the same amount of sodium chloride, if I took 1 mole of sodium chloride and dumped it into the solution, and I took 1 mole of calcium chloride and dumped it into the solution, they would both be 1 molar solutions. Well, assuming this was a liter of water, they would have the same concentration of formula units. But if I looked at this solution, the calcium chloride solution, this would have twice as much chloride as the table salt solution, the sodium chloride solution. It would have exactly as much calcium as it had sodium, right? There would be the same amount of molecules of calcium, but there would be twice as much chlorides in here because there were twice as many in the formula to begin with. Okay? So that's something to think about. So assuming they both dissolved completely, this would be a much stronger solution of chloride than this one would be. Now, let's keep going. If I had those different types of the different concentrations of solutions, they will actually affect the water differently. So water, normally, if we just took pure water with nothing in it, nothing dissolved in it, it has some properties that we associate with water. For instance, it boils at 100 Celsius. It freezes at 0 Celsius. And pure water is a very poor conductor of electricity. And I know that might sound counterintuitive because everybody tells you to avoid, going into the water when there's a lightning storm. But if it was really pure water, you probably would well, I'm not going to encourage you to go out into the water in a lightning storm, but pure water does not conduct electricity very well. And that's the reason, because most water molecules, or all water molecules, are covalently bonded, and covalently bonded chemicals are poor conductors of electricity. You really need ions to conduct electricity. So if we go back here to our salt solutions, a salt solution of sodium chloride is actually a much better conductor of electricity because you have all these positive and negative particles that are free to move around in it, and the same is true of calcium chloride. But if I looked at this salt solution versus this salt solution, I want you to think about the fact that this salt solution, even though they had the same amount of moles of each starting material, this salt solution contained twice as many moles of chloride as this salt solution, and thus this salt solution would actually probably conduct a little better than this salt solution because it has increased amount of ions, and the more ions you have, the better you are as a conductor, usually. So we would say things like, the greater the concentration of dissolved ions, the better the electrical conductivity. What about the boiling and the freezing? Well, there's an interesting effect, and you can measure this if you choose, and we might do a lab on it at some point, is that while normal pure water freezes at 0 Celsius, if I were to dump some salt into it, the freezing point would actually decrease, maybe down to -1, -2 or something, or even further, depending on how much of this solute is dissolved into the water. So let's go back to my salt solutions. This sodium chloride solution, if I put in some sodium chloride, would actually make the water freeze at temperatures lower than 0 degrees Celsius. And the same would be true of the calcium chloride. And just like we talked about, since there's more chloride ions in the calcium chloride solution for the same amount of starting material, this would actually make the freezing point of this water lower than if I had just used that same amount of sodium chloride. So increasing the amount of ions actually lowers the freezing point. And so what you will see sometimes in places where snow is very heavy, they will take salt crystals and they will put them into the streets, or they'll put them on the sidewalk. And when you put salt crystals on the sidewalk, it lowers the point at which the water freezes, and it can actually help melt the snow. Because while the snow might be frozen at 0 degrees, when you add the salt to it, now 0 degrees is not enough to freeze the snow. All right, and it helps melt the snow. So if you've ever heard of somebody salting the streets when it was snowing out, that's what they're doing. They're trying to keep ice and snow off of the sidewalks or off of the streets. It makes it easier to drive, makes it safer to walk, etc. Now, so let's make a statement about that. The greater the concentration of dissolved ions, the lower the freezing point. Of the water. What about the boiling point? Well, the exact opposite happens in terms of the boiling point. If I were to look at my two salt solutions here, I would find that instead of boiling at 100 degrees, they would boil it somewhere above 100 degrees. It would actually stay liquid longer if I was heating it. All right? And you would find that the calcium chloride would actually have a higher boiling point for the same amount of solute particles than did the sodium chloride. So the more chloride or the more solute particles I can dissolve in there, the more ions in the solution, the higher the boiling point would be. So this is called boiling point elevation. So the greater the concentration of dissolved ions, the higher the boiling point. And there's an equation, it's called the Clausius-Clapeyron equation, that you could solve to actually calculate, based on how much salt particle you dissolve, how high does the boiling point go. We're not going to get there in this particular class, but if you're interested, you could look it up. If you take AP chemistry, you'll probably be using it. It's not super huge. Some people will think that, for instance, when you go to cook pasta, a lot of people put salt in the water, and there are some misguided claims on the internet that the reason you put salt in the water is so that you can, the water when it's boiling will be at a higher temperature, and that way you cook the pasta faster. This is not correct. Well, it is correct that adding salt to the water increases the boiling point, but for most pasta dishes, the amount of salt you put in is probably only going to raise the temperature of the water about 1 or 2 degrees at the boiling point. So if you boil at 100 Celsius versus 102 Celsius, the quickness with which your pasta cooks is not significantly different. Most people add salt to pasta water for the taste, because you want your pasta to have some salty taste to it. But nevertheless, this does happen. So at really high concentrations, you could significantly increase the boiling point of your water, if that was something you decided. Okay. So to summarize, you have the more ion, when you dissolve your ions in solution, you can write a net ionic equation, and that would show you how many moles of each ion you're getting when it dissolves. And certain chemicals that have more ions to let go of will create higher concentrations of ions in solution. Once you have that solution, it will affect things like, it will affect how well it conducts electricity. A greater concentration has a greater conductivity. A greater concentration will boil at a higher temperature and will freeze at a lower temperature. Okay.